Okay, so this is problem 6.4. So in this problem, so we have a current carrying wire, and then we have a rectangular circuit next to it. The rectangular circuit is moving away from the current carrying wire, and it has a constant velocity in the y hat direction, and we're asked to figure out I2. So we have a current carrying wire, and when we have that current carrying wire, we have a B field. So this is just the equation right here, this first part, for a general B field through a wire. And this is the equation where R is less than L, essentially. So just go ahead and go back and look at 5-3.4, I think, just for that explanation. That basically just means that we have a very long wire. So it simplifies this equation a little bit. So this is just a general one that we pulled from 5.3.4, or if you look at example 5-3, just for notes. Okay, so just taking that as a given. Okay, so we have the B field that's coming from that wire. So we need to figure out the direction that that B field hits I2, because we're trying to find I2. So we're looking at this wire, so we're zooming in, and at this wire we want to know how the B field is affecting it, because that's going to affect how the current's induced. So B field is radial because of the right hand rule, so thumb in the direction of the current, B field in the direction that your fingers are wrapping around, and it's going to hit I2 in the negative x hat direction. So if you kind of look at the circuit, you should be able to kind of see that. But it's just going in the negative x hat because this is positive x, so negative x would be back. Okay, so that's our B1. So our B1 is the B field from this wire at the point that it's hitting I2. Okay, because we want it where it's hitting I2 and inducing that current. Okay, so we have this. We have our B1, and now to find the total induced EMF in I2, we're going to take the velocity of this loop, right? Because this loop is moving away. We're taking the velocity of the loop, so V2, which is like the second loop, crossed with our B1, so our B field coming from this wire, and then we're going to dot it with DL2, and DL2 is the length from here to here across I2. Okay, so just looking at that, like the piece of wire close to the inducing current. Okay, so now we're just going to kind of plug in our variables here. So I kind of wrote them out here. This is actually the solution for DL2, so we're going to integrate for it. So, okay, so our DL2 here, it's DZ in the Z hat, right? Because we're changing in the Z direction, right? For our DL. And then for B1, we talked about this, right? So we have the general equation for current through a wire for the B field induced by, or the B field created by a current through a wire. That's in the negative x hat direction. And then we're just given this velocity in the y hat direction. Okay, so those are the pieces that we're plugging in. Then we are just kind of going to simplify a little bit here. So we have y hat cross the negative x hat is going to equal z. If you have trouble visualizing that, you can just look at your coordinate system. So y hat crossed with the negative x for the right hand rule would be in the z direction. Okay, so now we have this piece simplified. So z dot dz in the z hat. And then the bounds for this dz, because it's this section for I2, the bounds for that are going to go from 0 to h. Okay, so we can drop out these z hat terms because dotted with each other, they're equal to 1. And then we end up with this for our v naught. Now the last piece that we need to look at is this r value. Okay, so this is important because, so when we have this second loop, r for this general equation that we took for the B field, this r is the distance from the charged wire to the point where the B field's acting, right? So we have this first line that it's acting on, but it's also acting on this part of the circuit, and that's going to contribute to our overall induced voltage. So we have here and here, right? So what we're going to need to do is basically bound r. So we're bounding it from D to D plus W, okay? So we're moving across the loop, essentially, okay? So so that's going to turn into 1 over D minus 1 over D plus W for our voltage here, okay? And this is our general expression for VEMF. And then to be able to find I2, all we're going to do is just divide it by the resistance that we're given, because there is a resistor in this second circuit. So just basically KCL over here, V over R is equal to I, okay? So the takeaway for this problem is we have a B field, and as we're moving away from that B field, the motion of the circuit is inducing a current and a VEMF in that second loop.